Good morning, everyone. In today's lecture, we will explore the architecture of Ultra Cyclone 2 FPGAs along with comparisons to Apex 20K and Stratix FPGA families. We will learn how modern FPGAs are structured internally and how different components like logic blocks, memory blocks, DSP units, and input-output systems work together to implement complex digital systems in FPGA. So, now we'll discuss about the Cyclone 2 architecture of FPGA functional blocks. Let us go to the slide. This slide will outline the architecture of Cyclone 2 FPGA. So here we can say in the diagram you can see there are the logic array blocks, flip-flops, embedded memory blocks, DSP blocks and input-output elements. Now we will explore each one by one how they are functional in the FPGA. So coming to logic array block, in short we can call as a LABS. So these are the fundamental unit. Inside each LAB are the logic elements and inside those are lookup tables. We know lookup tables are nothing but they contains the truth tables and the flip-flop will store the binary data across the clock cycle. Also the LUTs will contain the combinational logic blocks like AND get, OR get, etc. Apart from logic array blocks, we have the embedded memory blocks in the Ultra Cyclone 2 architecture. So what are the function of this embedded memory blocks? So these are normally flexible in nature and these are the memory cells. So why these are memory cells? Because these are the memory cells which can be configured as RAM. That is either it can read or write memory. They are embedded in the FPGA. So it also contains the ROM. What is ROM? That is read-only memory. These memory blocks are helping in storing temporary data or constant needed in the computation in the FPGA functional block. Apart from LABS and embedded memory blocks, we have other blocks such as DSP blocks. In what are the function of the DSP block in a high-end version? Suppose we are going for the customization of high-end version of FPGA, we will get the dedicated DSP unit, which are hardware blocks and they are optimized to perform fast arithmetic operations like multiplication and division and are also used in image processing and audio filtering in communication system. So what are the function of DSP blocks? These are helpful in high-end computation like multiplication, division, and also where we require the processing of images or digital signal processing elements for the communication system. DSP plays a vital role in the FPGA block. So this particular function we can find it only on the Cyclone 2 FPGA architecture. So what was the other more architecture? This was the Xilinx, but in the Xilinx you will not find the DSP blocks. Coming to input-output elements, these are the connection points that allow the FPGA to interact with the external environment, whether for sending signals to displays or receiving data from the sensor, and also they are used in the interfacing to the outer devices. In other hand, the input-output elements will also support different electrical standards and speeds, making them highly configurable. So what is the difference here we find in the Cyclone 2 architecture? Here we have the embedded multipliers. Also we have logic array blocks and DSP units and the input-output elements. Now we'll explore one by one. The Ultra Cyclone 2 architecture is composed of various functional blocks that enable the implementation of custom digital logic circuits. As we discussed, logic array blocks are nothing but they contain the lookup tables which can implement combinational logic functions such as AND get, OR get, and also the flip-flop to store the data and the information. And apart from that, we have the embedded memory block in the Cyclone 2 architecture, which have the RAM or ROM. RAM is for random access memory and ROM is for read-only memory. These memory blocks can be used for storing data, and who will store the lookup tables which are already in the logic array block. The embedded memory blocks in turn will store the lookup tables and for other purpose. Apart from that, we have DSP block. As I have already explained in the previous slide, the DSP blocks are nothing but they are used for high-end computation in the FPGA block for processing the DSP algorithms, digital signal processing algorithm or image processing algorithm. For we can use the DSP block. Also, it is used for multiplication, and division. Apart from all this, the common element of all the architecture of FPGAs are input-output elements, which are used to provide connection to external world, means to interface the input and output to the external devices with the FPGA board, which can use for sending the signals from one end to other end and also to get the output. So here we can see what are the normal key features of Cyclone 2 architecture of FPGA. Why we are going for Cyclone 2 architecture rather than Xilinx? What are the main advantages of this particular configuration? And mostly Cyclone 2 architecture are used in the academic and industry projects. But why we are using? Why we are not going for Xilinx and why we are going for the Cyclone 2? They have some specifications like they are highly consuming low power, means these are low power consumption devices while maintaining high performance, because in any electrical appliances we need to have devices which can consume low power but the efficiency should be more. So in this architecture we have the low power consumption and also high performance, which can be ideal for portable also, means it can be portable, it can be moved in hand by from one place to another, and also for embedded related applications. Apart from that, one more advantage is that due to small IC size, it can be portable. Also, it contains 68,000 logic elements, 250 memory blocks, and 150 DSP blocks, which can support large scale digital system. That means it can contain more data and storage power as compared to the other architecture of FPGA. And also there are 622 input output pins, which can give a flexibility to connect with the too many peripherals or too many systems. So at a time we can do more and more processing of algorithms in the Cyclone 2 architecture. Also, it contains PLL, that is phase lock loop. These are nothing but they are helpful for generating clock frequencies internally for maintaining the timing constraint in any sequential or combinational circuit or any bigger high-end system. Clock is a utmost necessary signal for maintaining the time constraint. So how it can be maintained? By using of the phase lock loop. So in total it has 4 PLL, which can be used for maintaining timing constant and also for timing applications like communicating from one end to other. So these are the key features of Cyclone architecture where we are using for academic and industry project related. In this slide, we will detail learn about logic element, that is logic array block architecture. Here you see already I have discussed LAB contains LUTs. So what are the LUTs? These are the lookup tables which stores the logic function as a truth table and also contains many combinational circuits. So each logic element will include a LUT which store the logic function as a truth table, and also flip-flop which will store the memory and the state, that is S0 state, S1 state, and so on. Now, how each LE will be connected to one more LE, because there are a lot of LE in the lab. So we have local routing resources in this lab architecture, which will help from communicating from one LE to LE within and across the logic array blocks. So when we program an FPGA, this whatever the code we are writing and dumping into the FPGA will be get mapped to LEs. So only we can get the proper output signal. If the LEs and our code is not being mapped, then we will not get a proper output and then we will get a error. So the code and the LE should be properly mapped in order to process the code and get the desired output. And due to this, LABs are helpful for synthesizing the tool for configuring the logic array blocks according to our requirement, according to our specification. Whatever the code we will write in a Vivado tool, those signals, those input ports, output ports, the specification should be mapped in the respect to this. Now, in detail, in this slide, we will know the LUT architecture. Already we have discussed that is the LUT, that is lookup table. So, lookup table architecture we will see. So, what is a lookup table? As already you know, it is a small memory unit which will allow to implement any Boolean example. Boolean logic, that is either any Boolean logic. For example, if we need a two input AND gate. So, the LUT will program with the two table for AND. That is two inputs, one outputs. It, as per the logic of AND gate, if two of the inputs are high, then only the output is high. Already we know those data will be stored as a two table in the LUT. So if we need a two input AND gate, LUT will program with two table for AND. And if we in practice we require four input or six input LUTs are also used, providing a wide range of logical configuration. This reconfigurable nature is what makes FPGA is very powerful and flexible for hardware designers. Coming to Cyclone to input output block architecture. One by one, we are discussing about the internal and detailed structure of each block. So what are the input output block? These are the block where internal signals means the outside peripheral device. That means the internal signal, whatever the are there, will be connected to the outer systems like processors or systems. So it handles combinational input. That means it directly receives external signals into the FPGA suitable for simple input. One more we have a sequential input or output which uses flip-flop to synchronize with the system clock. So sequential input output is critical for applications requiring timing control like capturing sensor data or communication over SPI. Combinational output will generate immediate output based on current logic state. In other than that, we have state buffer, which are used when multiple components share a data bus, which will allow only one to drive the line at a time. So these are useful for the input and output block. So in short, we will learn in this slide input output blocks often consist of combinational input, sequential logic, and combination output combines along with the optional tri-state buffer functionality. So combination input, it is used for responsible for accepting external signal as input. Sequential input, sequential output, it contains the flip-flop or latches to store the memory, and also it is used to synchronize with the clock signals with the input or output data. Apart from that, combinational output. So the input output block can have combinational output which will generate the output signal based on the current state. And optional, we have the tri-state buffer. Now this is the Apex 20K family basic structure. So these are more advanced Ultra FPGA, and this in all total we have others. So please have a look on this Apex 20K family basic structure. Coming to Apex 20K overview, in short I will explain. It supports more complex designs with 51,840 labs, 216 embedded memories, and 808 input output pins. So the memory, you can imagine, it can store up to 4 MB, making it suitable for systems requiring large buffers or configuration storage. And apart from that, we have 4 PLL which are included for robust clock generation. So importantly, it has dedicated carry and cascaded chain. These chains are hardware shortcuts for arithmetic operations like adders and counters, making them faster than implementing the general purpose logic. So just you can imagine how efficiency and better computational facility we have in the Apex 20K family. Apex 20K FPGA is a high performance device which can implement more complex digital functions. As already I have discussed, it has 51,840 labs, that is logic array block, 216 embedded memory block, making it more efficient for the high-end computational. And the embedded memory block can maximum can store 4 M bits of data. So this is the Apex 20K family mega lab structure. Now we'll discuss how this Apex 20K architecture is met. The architecture is organized using mega labs. In other architecture, we have learned only the lab set is logic array blocks, but in Apex 20K architecture is the more advanced version where we have the mega labs. Each mega lab will contain a set of labs and embedded system block, that is ESP and interconnect. So it also contains fast stack interconnect which can run across the device, enabling high speed routing of signals between the logic areas. So each LAB includes 10 LEs with their own LUT, flip-flop and local interconnect. These local interconnects allow communication between or adjacent to labs, minimizing delay and improving routing efficiency. This is the structure of Apex 20K family. We have carry chain, carry in. Just like Cyclone 2, Apex IO block includes combination input, sequential logic, and the combination output and optional tri-state buffer. Combination inputs are for simple signal reception, means they use for receiving the signal, sequential logic for registering the data, storing the data, example flip-flop and latch, combinational output, and optional tri-state buffer. This is already I explained in the previous slide. This is the Ultra Stratus FPGA overview. So Stratus is a high-performance FPGA family designed for heavy-duty application. With over 1 million labs, 6 many DSP blocks, and 230 pins, it can handle AI, video processing, or 5G baseband. It also includes 308 MB of memory and high-end DSP resources. So this architecture features a rich mix of programmable logic, embedded memory, and high-speed input-output, perfect for SoC design, that is system on chip designs. Similarly, this is practice lab architecture, each one by one. These labs here are similar in principle but more optimized for high-speed operation. Each lab in the sense logic array blocks include 10 logic elements which are used for advanced routing and pipelining, allow faster data flow. Now it also have design tools like advantage of static layout to place timing critical logic optimally. So this is a static FPGA LE architecture, means logic element architecture. Inside each LE will have a LUTs which will handles the logic function and have a two table and have a combination circuit. Apart from that, flip-flop example sequential circuit, flip-flop registers will store the results. Also, this static add advanced control logic for clock gating, asynchronous research, and data enable, which helps in power optimize and performance tuning. So just have a look for the strategy FPGA. It have a combination logic, adder, register, and the output. This is the static FPGA input output block. Again, we have a familiar structure just like the before structure, that is a input output block of static FPGA. We have a combination input and output block, sequential logic inside input output buffer, including data handling, tri-state buffer, which are crucial for data buses and shade line. In Structis, the extra feature is that this input output block also support high-speed signaling standard like LBDs or STLs, enabling use in communication and data acquisition system. Just have a look for 1 minute. Input output often consists of combinational input, sequential logic, and combinational output components along with optional tri-state buffer functionality. Combinational input, this part of the input output block is responsible for accepting external signal as input. These signals are typically treated as combinational logic units. These signals can be used for various purposes like data input or controlling the signal. Apart from that, we have sequential input or sequential output. Inside the input output block, sequential logic elements like flip-flop or latches can be included. These elements will allow you to store and process input data or output data in synchronization with clock signal. Combinational output, after processing the input data using any required sequential logic, now we have to generate the output. So this input output block can have combinational output component. This component generates the final output signal based on the current state of the sequential elements and potentially the combinational input signal. Combinational outputs are used to drive the external devices or other logic elements within the FPGA. Tri-state buffer is optional. Some input-output blocks include tri-state buffer functionality. Tri-state buffer can be used to control the output of a signal by enabling or disabling it. So this is the end of the all the architecture of FPGA family with each description of lab architecture, input output block architecture, LUTs architecture, and also the logic elements architecture. So what we have learned today in this complete slides, Cyclone 2, we have to give a brief comparison. Cyclone 2 architecture will have entry level. It is great for sensitive or low power application. Apex 20K will have a mid-range suited for moderately complex systems with high interconnectivity. Practice architecture will have a premium RAM ideal for advanced DSP processing, real-time analytics, and hardware escalation. All will use similar architecture patterns, that is LABs, LUTs, flip-flop, DSP blocks, and input-output, but differ in the scale, performance, and supported applications. So in conclusion, in summary, we have learned about FPGA internal architecture focusing on Ultra families. Understanding how the logic array blocks, memory input blocks are structured helps you design better digital systems. Whether we are implementing a small counter or a full process pipeline, these building blocks are a very foundation. In our next lecture, we will look into some FPGA programming using SDL and real-world design examples. Thank you for your attention.